Okay, so we had ER here, we had EY there, we had EB there, and you say this point here is R. This is now we connected here, we connected R1 and Y. Here we connected Y1 and B. Here we have B1. So what we said is we connected these 2 points and we realized that the EMF across these points is 0. That means there's no current flowing here. So we are allowed to connect, and that does not affect this circuit, because if there is no current flowing, then nothing is really happening there. So we are allowed to connect those 2 points, because when you connect them, the EMF, the total EMF in that line, in this line here, is 0, which means there is no current flowing in there, which is fine. Okay. All right, so now this point we called it R, and we say that the end of B, we connected, the end of B here was connected to Y1. The end of B. So the end of B is going to be this one, which is connected to Y1. So I'm going to say this is Y1 and this is Y. So I'm going to call this EY. It doesn't really matter. I'll call that EY. I'll call this one ER, and I'll call this one EB. Is it so? So let's see if it's correct. So if this is ER, that means that this point here is R, right? Which is correct. This point here is R. So this arrow here is the one that is wrong, because a point should not have 2 arrows facing it. So this arrow should be there, and this one is also wrong. This arrow should be there. So let's see it now. So if this one is R, then here we're going to have R1. But at R1, is it so? Okay, it's fine. Here we are going to have B, this is B, sorry, this is B. Yeah, it's fine. R1 is connected to B1, and this one is Y. So then it's Y here. Okay. Do we see the connection here? So you must make sure that it's like it's a circle. It's like it's some sort of a circle. That's all it should be. When you're connecting this thing, it should be like in some sort of a cycle. So the arrows should be like in a cycle like that. So if you call this point R, then this one is going to be Y, and this one is going to be our B. Do we get it? Hello? No one wants to respond? Yes. Okay. So now the EMFs that are in these, now inside the 3-phase system, the delta system, these EMFs are going to be called phase EMFs. Yeah? We're going to call these ones phase EMFs. And the ones that we will now later, we are going to talk about EMFs on this, like maybe this one, we call it ERY. These will now be called line EMFs. Yeah, this is RYB, and then when you connect these two, we have ERB. So these ones that are outside, when you just put a voltmeter and you're connecting these 2 points that are outside here, we'll call those line EMFs or line voltages. But then when you're looking at if you are looking at hey, a lot of people are joining. If you are looking at the EMFs that are here, we'll call these phase EMFs. You understand? So these ones will be called phase EMFs, and those ones will be called line EMFs. All right. Okay, so let's also look at a star connection. I'll just explain this. I'm not going to go into the derivation like I just did with the delta. So this is the delta connection. delta, sorry, is delta. So I want to look at the star connection. So a star connection, we all know that we have something like that. So our coils are going to be connected like that. Okay. So if I call this point R, if I say this is my R, now you will see that the neutral point, the starting points, let me call this Y, and let me call this B. So this one is in 120 degree. This is 120 also. So you see that the starting points have all been connected at the same point. So that point is called the neutral point. They call it the neutral point. Now you will see that if you connect a wire in the neutral point, you realize that in most cases, the neutral wire, if you have equal loads, the neutral wire, we have zero current. We have zero current. I'll explain that one later. So here we have our ER. Here we have our EY. And here we have our EB. Okay. Those that are joining us, will you please mute your mics so that we don't hear the kids that are crying there? You know, we know your kids. All right, so that will be the star connection. Now, in the star connection, you must realize something. We have, in the star connection, we have also phase quantities. We also have phase quantities. So we have, this is our phase EMF here. And this is also our phase EMF. And this one is also our phase EMF here. So we have phase quantities. Then we also have line quantities. Now the line quantities, if I now take this line and put it here, I take this line, put it there, and then I also take this line, I put it there. From here, we'll get our line quantities. So you can just measure, if you measure the voltage across these two lines, you're going to get the phase quantity EBY. And you're going, if you measure between these two lines, you're going to get the phase quantity EYB. Now, I want you to check the notation. So this one is supposed to be RY, sorry. Check the notation. Because R is in front, I always say RY. And here, because Y is in front, I always say YB. Remember the phase differences that we talked about first. And then if I do this, I will have ERB, or sometimes they call it EBR. You will see as we call, because you know, in terms of phases, one thing can be, you can express it as it's in front in another way. Okay, let me not explain that, I'll confuse people. All right, so these will be the line quantities, and these are our phase quantities. Okay, so now it's very important when you're dealing with these multi-phase systems to understand what is your phase quantity, what is your line quantity, and how you manipulate them when you're doing your calculation. So that is where I want to go straight away, because these other derivations, you can just check them in the book. So I wanted us to look into these to see what is the relationship. If we are looking at a delta connected circuit, we want to know what is the relationship between the phase quantity and the line quantities. So when you're saying phase quantities, we are going to have voltage and we are going to have current. So we have line currents and we have phase currents. So you want to know what is the relationship between the line current and the phase current? What is the relationship between a line voltage and a phase voltage? So for both of these, we are going to do that. All right. So that's where we are going into now. It's just a small derivation. It needs you to remember phasors. It needs you to remember phasor diagrams. So phasor diagrams are not going to leave our lives. They are going to be with us. So I'm going to start with that, and I'll look at I'll look at the star. Let me just start with the star first. Yes. Let me just start with the star first. Okay. Let me go to the next page. So if we have a star connected circuit, pardon my handwriting, this is not easy. Then this it's called a neutral, and here we have Y, and here we are going to have our B. Okay. And now I no longer want to work with instantaneous values. So when you're not working with instantaneous values, what are we working with? RMS values. So instead of putting E, the small letter E here, I'm going to put a capital letter E, which is R. Now this is representing the RMS value. You must make sure you understand that one. And here we are going to have RMS value EY. Here we are going to have RMS value EB. So our goal here is to find the relationship between the phase EMF and the phase, EMF and the line EMF. So let me say now, here, I want to find the voltage between these 2 points. So you can already see that the voltage between these 2 points is what we call the line voltage. So if I call that line voltage, if I call it E, because now I'm coming from Y, going through to R, I'm going to call it what? What should I call it? Let me just call it E, Y, because it's going through point N to R. You understand this as we continue. You familiarize yourselves with them. So because I'm coming from Y through N to R, I'm going to call this E, Y, N, R. Okay. So if I want to find this now, this is a phase, this is a line quantity, and here we have phase quantities. So if you want to find this one, it's easy. All you need to do is you take your KVL, because our KVL is still applying, because this is a loop. Okay. So if you take your KVL and you write that loop, you are going to see that you are going to have, now if you move like that, you're going to have a negative E, Y plus E, R minus E, Y, and R. In the end, we will remove the N, we just call it YR. Y and R, which is equal to 0. So I've taken the KVL here. All right. Now that means I want to find this guy. So if I take it the other side, it means that my Y, my EYNR, which is our phase quantity, is equal to ER minus EY. Okay. Now these are, let's write these as phase quantities. Phasors, sorry, phasors. So we want to write these as phasors. Now, if it is a phasor, let's go back to the way we defined this at the beginning. We say the EMF that is induced in R, we said we take that as the reference. And when you take it as the reference, we say, but it was up there. So we say the EMF here was ER, it was our reference. But the one that was Y was 120 degrees behind ER. So here we have EY, which is 120. Let me use a different, for my Cartesian system here, I'm going to put a Cartesian system there and there. So here we see that it's 120 degrees, but if this is a 90, you will see that here we have an angle 30 degrees here. Okay. Now, according to phasors, remember these are phasor sums. When you're adding phasors, you have ER, but then we have a minus EY. This is a positive EY. So what did we usually do when you're adding this? We would find the negative of this. The negative of that will be going in this direction. Okay, so this is our negative EY. So we are going to add these two. How do you add the two? Remember, you take this phase and you go and put it in front of that one, parallel, and you take this one, you go ahead and put in front of that one. So where they meet is where this quantity is going to be. So that quantity is going to be somewhere here. So this is our phase quantity. This is E, Y, and R. Okay. Now we just do. We can use your Cartesian, your knowledge on Cartesian coordinate systems. We can resolve this because our goal is to find the value of this guy. Okay. So what we have to do is you can resolve this. If you had numbers, you would just use, you know, those phasor sums where you change from rectangle to polar and then you do the calculation. But right now, since we are deriving, we don't have numbers. We have to use what is that, general terms. So here our angle is going to be 30. So what should we do for us to get this value here? Now, remember we said these phase quantities or these wires are between the same magnets. That means they have the same quantity. The RMS values are actually the same. So we are saying that the magnitudes of the RMS values, remember, magnitudes. So we are taking magnitudes. Here it's a phasor sum, but if I'm talking about magnitudes, I want the value. So the magnitudes are the same. Okay, keep it somewhere. I'm going to use it now. So if I want to find this value, all I have to do is, if this is a 30, what should I do now to get this one? It's mathematics now. So I can say this cos that. If I cos this one, it goes here, and sine it goes there. Then I will take now the verticals and the horizontals, and then I add them together. So I can just say my E vertical here is going to be the sum of, we're going to have ER, these are magnitudes, remember, ER here, and then this one here now. This, we don't take this negative, don't really use it. I just put it out there so that you see it's the negative of this one. So I'm going to have ER. We don't have to resolve this one because it's already in the y-axis, but we have to resolve this guy. So if I resolve this guy, I will see that I have to add what? Plus EY, that is what, sine 30, okay? So this is the vertical. But since I said these two magnitudes are the same, I can actually do this. I can, since this is the same, I can say that ER plus ER, because since EY and ER are the same, I can just say ER plus ER sine 30. Yeah. Then here, if I solve this one, I can factor out the ER. Then I will have ER. Everyone knows what the value of sine 30 is. It's a half, so it's a 1 plus a half. This gives us a 3/2. Or if you want, you can write it as what? 1.5 ER. Let's keep it there. So this is the vertical components of this EYNR. Now, on the horizontal component, E horizontal, obviously it will be negative now. It will be a negative EY cos 30. Now, if you simplify that one, what is cos 30 again? Cos 30 is a √3/2. So I can say it's a negative √3/2 of EY. But we said we already know EY and ER are the same magnitude. So I can rewrite this as the square root of 3/2 of ER. So that's the horizontal and the vertical components. Now, what you will see is that if you then choose, to simplify to find this value, how do you find this value when you have the horizontal and the vertical? We just use the square root, Pythagoras theorem. So our I derived it in a different way from the way it's done in the book. EYNR is going to be the square root of 1.5, so that I don't lose some people. It's going to be the square root of EV squared. The squared is on the E, squared plus EH squared. Okay. All right. So that means we are going to take this one and square it, and then we take this one and square them. Then we add them together. When we add them together, we then find our answer. So let's do that. So we have 1.5 ER and a negative root 3 over 2 ER. So our EYNR is going to be equal to the square root of 1.5 ER squared plus the negative over root 3 over 2 ER squared. Now, if we continue with that one, we are going to have a square root of, now what is this, 9 over 2 it's actually 9 over 4, sorry. It's 9 over 4 ER squared plus, this one will give us a 3 over 4 ER squared. I hope it will give me the correct answer. So you can see here, I can factor out ER squared. But for the sake of those that might not see it, I'll have ER squared bracket 9 over 4 plus 3 over 4. Yes, it's giving me the answer that I want. Okay, so here you can see that I can cancel here. So I can cancel that. Then I'll remain with, if you add this 9 over 4 plus 3 over 4, you actually get a 12 over 4, which is the square root of 3. Yeah? And then this one cancels the ER, then you get ER. Beautiful. So that means our answer is going to be the square root of 3 ER. So we're going to make our conclusion now. So EYNR is going to be the square root of ER. Now let's go back to the first page. Here, let's check here. We say that EYNR is called our line quantity. So I can go back here and say now, so this one, I'm going to call this VL, the line voltage, because it's a line quantity. Then if we go back again and we check what ER is a phase quantity. So I can go back to this and say, okay, so now this one is a phase quantity. So I can say my line voltage in a delta connected system is equal to √3 multiplied by the phase quantity. So this is what we wanted to derive. So in a delta connected system, the line voltage is equal to √3 of the phase voltage. Sometimes in the books they write 1.73. They just simplify the √3. Okay. Okay. Do you get it?
Comma.
Yes.
Comma.
Mm-hmm.
Can you please say that what you just circled now, that VL equals to, can you say that again, like in words, what you said before?
Okay, I'm saying now, VL is the line voltage. When we say line voltage, we are talking about the wires that are outside here. These wires, these are the wires that we see. Yeah? So when we say the voltage between these two lines, that's what we call the line voltage. So this line voltage, we wanted to see the relationship between this line voltage and the phase voltage. So now this derivation has shown us that the line voltage is equal, in a delta connected system, the line voltage is equal to √3 times the phase voltage. Do you understand?
Okay.
Okay, the rest, you are quiet.
Thank you.
Yes, Joseph.
I have a question.
Joseph's network is poor.
Just go to the previous slide.
Okay, Joseph, can you type your question because your voice is.
Can you hear me?
Type your question, Joseph.
Okay, I'm saying go to the previous slide. Can you hear me?
Okay, I should go to the previous slide. I'm even running out of time again. We are left with 10 minutes. Just type your question.
Can you hear me now?
Yes.
Question is too long, man, to be typed.
Okay, just try.
Can you hear me?
Yeah. Now you are not speaking.
Okay, I wanna ask with regards to the derivation that you got me for R.
Okay, I think let's do this.
Now, can you hear me now?
I think now the problem is your network is connecting and disconnecting. What we can do is I'll address your question later. Let's just finish this and then we'll see what we can do. Okay. Or if you got it, then it's fine. All right. So this applies to everything. So even though I used one section to derive this, it will also apply. If you come and check here, it will apply. If you come and check there, it will also apply. Then the other thing that you will see is what is it? If you do the calculation properly, you should see that the line voltage will lead the phase voltage by 30 degrees. So we have a 30 degrees here. Here we are going to have a 30 degrees there. So you'll see that the line voltage will actually lead the phase voltage at R by 30. So when we do if you finish this diagram, you see that you will have the line voltages like here. If we say this is why we look at this R. If we consider this R and that R, you see that this line voltage here is going to be in front of this phase voltage by 30. Then if you do the constructions again, you see that the line voltage between Y and sorry, I didn't draw the other one, and B, it will also be 30. It will also be 30. So you can just follow. You can finish the whole derivation, follow every other phase voltage. You will prove the same thing, but you will see that line voltages will lead the phase voltage by 30 degrees. Okay, let's also talk about the current. Now the current is easy. The current is very easy because check here. The current flowing here, I'm going to call this IR. Now this one, I'll call it my phase current. The current flowing here will go through this coil and then it will also go out here. So it is simple to see that the line current in a star connected, I was always saying delta, no, I was making a mistake. It's star connected. In a star connected system, the phase current is equal to the line current here. Okay, because it's one line, as you can see. So the phase current will be equal to the line current. So line currents are found, you are looking at this line, and what is the current flowing in that line? And even if you check here, if you have I, Y, it will be the same as the line current flowing here. If you have I, B, it will be the same as the line current flowing in this line here. So line currents are going to be the same. So to summarize this, in a star connected system, you can just, in a star connected system, the line voltage is equal to √3 of the phase voltage. And the current, the line current is equal to the phase current. That's the summary. It's simple. This you need to remember, because when you come to delta, it will be different. So this is a star. When you come to delta, it will be the other way. Okay. So all you need to know is, if you are looking at a star, just know that, okay, the line is the same. I mean, the line currents, the current is the same. Then it is the voltage that is multiplied by √3. Then when you come to delta, you will see also the difference. Okay. So because our time is almost up, these Zoom people even changed the time to 30 minutes now. It has gone down, so I have to pay if I want to make longer videos. So I hope you understood this one, because we still have to do a derivation on when you look at the delta, then we see how the phase quantities of a delta relate to the line quantities. And then we also have to work some examples. But I think from now on, I think it's the best for me to just do those pre-recordings and then give you the link. How do we see that? Everyone can unmute now, so we talk, because the class is off. We have
Yes.
3 minutes to talk.
I'm lost. Please repeat what you said.
I'm saying we have 3 minutes to talk. I'm saying, don't you think it is good for me to just do the pre-recordings, then send you the link, other than us being online? Because I think maybe the network, sometimes if we are a lot, it might just play with our
Yeah, do the pre-recordings, because I got kicked out just now, so I missed a lot.
yeah, you see. So yes, Sakunga.
Yay! Guma. I don't mind, but I do agree with Emmanuel. Like, it does, like, for some of us, the network goes and then we miss parts of the
section. But it's always good, because the video is always going to be there. But I think the pre-recordings are fine, though they might have a problem where you wanted to ask a question, you will not be able to. But we just have to use questions. You just have to address the questions after you've seen the video.
Wouldn't we be able to use both? Like, let's say we use the pre-recordings, and then we have a session where we have live video, and then we ask our questions and stuff.
Okay, I think that one is also fine. Maybe we can, maybe in calculations, I don't know what. Yeah, we can do that. Yes.
I think we can do like the pre-recording stuff, and then we can go on like the Zoom or MS Teams when we are doing like examples and exercises, so we can ask questions.
Okay.
Yeah.
All right. And the others, we are about to be checked out now.
The others already switched off their lights. Let's just go sleep.
All right, guys. Have a good night.
Bye, Goma.
Bye.
Sharp Goma.
Sharp. Dorian. Dorian was here.